Have you ever wondered how your phone knows which is the way up? Or how drones stay perfectly balanced in air? It isn't magic, it is all thanks to these incredible devices called inertial sensors. In this video, we're gonna look into what inertial sensors are, how they work, their magic, some cool applications you probably use every day, and best of all, a simple experiment with the hands-on exercise to see them in action. When we're talking about inertial sensors, we're usually talking about two main types: accelerometers and gyroscopes. Start with accelerometers. As the name suggests, they measure acceleration. If you recall Newton's first law, it summarizes to the following: if an object is at rest, it will remain at rest. If it's in motion, it will remain in motion, unless stopped or altered by an external force. And accelerometers, they exploit this. Now imagine a very tiny ball and a very tiny housing. And the housing is connected to the ball with tiny springs. When the sensor moves, the housing starts moving. The tiny ball will resist the motion. And because of the springs will detect the difference relative between the ball and the housing. That difference is encoded into a capacitance difference, and that difference in capacitance translates to a difference in voltage, and the difference in voltage is something that we can measure. This technology is known as microelectromechanical systems, or MEMS. Modern accelerometers often measure accelerations with respect to its own three axes: X, Y, and Z. So boards like this, they would measure accelerations in this direction, and this direction. It is also very common that they print the axis to which, relative to which they do the measurements in the board itself. The fact that those sensors can measure acceleration in three axes is exactly why they can detect where the gravity vector or the force of gravity is. Because if you know where the gravity is, you also know where the up is. And that's how your phone knows how to switch between landscape and portrait mode. Next, we have gyroscopes, or gyros for the close friends. While accelerometers measure linear accelerations, gyroscopes measure angular velocities, which is how fast an object is rotating around some axis. The working principle for gyroscopes is a bit different. They use the phenomenon called Coriolis effect, which is the fact that if there is a mass moving with a certain velocity, if you apply an angular motion to that mass that is already moving to a certain direction, there will be a force perpendicular to the motion of the velocity. So a force like this. That force is what the gyroscope's transducers can detect. So in essence, it is also detecting the resistance of motion with mechanical systems. It is super clever. So accelerometers are all about linear motion and accelerations on those axes, while gyroscopes are all about rotations, angular motion, and in that we can measure velocity. And this is exactly what we can extract from those sensors: linear accelerations and angular velocity. And if you ask me, I think it's so cool that with the simple software interface that we're gonna look into later on, with an I2C interface, we can access that kind of technology simply by transferring data between a device and a computer. That's so cool. Just to name a few of the applications that we can unlock with accelerometers and gyroscopes, inertial sensors. We can name smartphones or tablets. With those kind of sensors, they can detect orientation, they can detect if they have fallen, and much more. Of course, we have to name the drones and robotics in general, because those sensors are so powerful, they are so sensitive to motions in general, and because those kind of applications, they often rely a lot on motion. They have to know where they're going, they have to detect if they have been perturbed, they have to detect if there is something disturbing the control loop. So those sensors are essential for robotics and drones. Automotive also uses a lot of MEMS sensors to detect orientation, also to detect sudden spikes of deceleration to trigger airbags. It's a powerful sensor to provide that insight. Fitness trackers, smartwatches cannot live without inertial sensors. There's so much they can tell about how your arm is moving or how your body is moving, depending on the exercise that you do, depending on the sport that you do. They have predefined patterns to best detect and best track how much energy you are spending on your exercise. They can also count steps. They're used to count steps. They are used to detect if people have fallen for healthcare and and so much more. Virtual reality, augmented reality are also very good examples because they have to access motion information on the person using the wearable. The system has to be aware of at all times of where the person is looking at to render different things. So it has to be precise, it has to be fast, and has to be smooth. There are many other applications. We could spend a whole day here naming those applications in industry, home appliances, and everywhere. Those sensors are essential, they are everywhere, and they are powerful, incredible little devices. I really like them. But enough about theory, let's get practical. In today's experiment, I'm gonna show you the process of exposing the inertial sensor data to pretty much any user you can think of, or any clients that you can think of. In the previous video, we've seen how to do that for LiDAR sensor data. And today we're gonna do the same for inertial sensor data. And for that, we're gonna be using, you guessed it, gRPC. I like gRPC because it allows us to establish a well-defined interface definition file. This interface allows the gRPC framework to generate all the infrastructure for us in any language. So that helps a lot on discussions, it helps a lot on infrastructure, data handling, data transfer, protocol, types, a lot of stuff. That's why I like it so much. And it's fast. Now I must say, a really good alternative for today's experiment will be to use ROS, Robotic Operating System. But that's beyond the topic of today's video. The most important part is that we go to the process of extracting information from a sensor, and that information is exposed via file-defined interface that many people can access, consume that information, and do whatever they want with it. The inertial sensor that I selected is this one, ICM 20948. I'm gonna confess there is nothing too special about this one. It is just a sensor that is readily available where I live. I could buy it easily, let's put it like this. But I'm sure there could be other more popular choices like the MPU 6050 or BNO 055. It doesn't really matter because the way you're probably gonna realize here is that we rely more on interfaces, and the inertial sensor is basically a thing that we could abstract away, and then it doesn't really matter the detail, it as a detail. But maybe in a different video we could just connect them together and see how they compare to each other. That's not a bad idea. And the computing device that it's connected to the inertial sensor to extract information is, of course, a very good and old friend, Raspberry Pi 5. The main reason I'm using the Raspberry Pi as a, let's say, a extractor of information is because I'm gonna host a server in the Raspberry Pi 5 from which I'm gonna consume the data from the inertial sensors as a client via the network. So in many cases, it might be convenient to use a microcontroller and just talk to the inertial sensor and do some kind of computation. But in our case, we're gonna just create the Raspberry Pi will act as a proxy of information. So it's a server serving data, streaming data continuously to some other application. Let's jump into the code. This is the design of our experiment. If you look at the top left, there is an interface that establishes the contract, the data type, the function, the methods that we're gonna have to agree upon. And that's what the driver will have to inherit and honor. So looking at that top left, we have an interface. We have a driver that derives that interface. It's an implementation of that interface. Then we have an application that will consume that or use that. And the data that is going to fetch from the driver, it's going to be passed to another object or class called gRPC server. That server have a function called publish IMU, which will hold the data. And there is another function called get IMU. That function get IMU is actually an implementation of the proto service that is a call that is called by a client to retrieve the IMU information or the inertial sensor data. What I want to highlight here is that we are using gRPC to serve the purpose of exposing inertial sensor data to any external part, which is represented by the sensor client object right here on the top right. So this guy can be any client, like I said. It can be a Python client, a web client, another C++ client, Rust client, Go client, doesn't matter. It is a client that just needs to know gRPC, and that's pretty much it. Now, a special attention to the struct here on the top left, the IMU data. And by IMU, I mean inertial measurement unit. We can also call inertial sensors IMUs. They are pretty much the same thing. And the contents are acceleration on the x-axis, y-axis, z-axis, so 3-axis acceleration, and angular velocities on the x-axis, y-axis, and z-axis. This is the only thing that we have to that the driver has to pass along the whole chain of calls. One last thing I want to stress is the gRPC server is an object. It is an actual class that we create in our application. If we start it, and it has two main functions. The first function is to retrieve information from the IMU. This means that someone else has to pass the IMU data to the gRPC server. This is done by the publish IMU. And the second thing is the get IMU. The get IMU is the implementation of the gRPC service. So this is something a client calls. Hey, I'm the client, you're the server. Please give me IMU information. And so I am, from that perspective, I am calling the get IMU. But here in our application, we have a class or an object that has both services. Someone has to put the data and someone will get the data. This can be collapsed into a single object, as you can see here. For today's experiment, I created a library in this repository. This library is supposed to be a very simple implementation of a way to expose sensory information in a generic way via gRPC. So I use the same library to expose LiDAR information via gRPC. I'm using the same library now to expose inertial sensor data via gRPC, so that any client that just needs to know about gRPC has sufficient information and can consume the data to whatever the need is. So back to the picture, you should see here on top. We look on the top left, and here we have just a refreshing of what the definition of our data is. This is the acceleration part. This is the gyroscope or the angular velocity part. Nothing too special. Here we see a class. This class holds the contract of what the drivers have to do. And right now it is very simple. All the driver has to implement is a function called getIMUData, and it has to return the same struct that we see here above. That's all. Nothing special again. The general advice I have is the simplest you can make an interface definition, the simplest the drivers will also be. So let's keep it simple for now. Now let's have a quick look at the driver. The driver implements this interface that we just saw. And here we can see specifics about how the driver works. We can specify, for example, this particular sensor module here. We can specify the range of measurements. Am I supposed to measure degrees per second up to 2000 degrees per second, or 250 is enough? So you can configure your sensor, and the driver should enable the caller or the user of this device right here to configure that kind of settings. One important remark here is that I am using a I2C communication protocol. This is basically two wires that you connect between a host and a slave. And the way I2C works is each device like this has a predefined address. So it has if you look at the I2C bus, you can talk to a device on the bus level. There is an address on the bus level, and the address for this device is specified in the datasheet. Let me just pull it up. Address is right here. Gonna be either depending on a specific pin. If the specific pin is 0, is one address. If it's 1, is another address. And if I have a master trying to communicate to a slave, one of the important things is the address. So first it finds a slave based on address, and from inside that slave we access specific registers, and the registers will contain all the information that we need, either to configure the sensor and to retrieve information from the sensor. That is I2C in a nutshell. Here, for example, there is a specific address inside that slave from which you can retrieve what is the gyroscope x-axis measurements, low byte, and there is also the high byte. So we can retrieve this in a 16-bit stream of bits. You get it out from the sensor using an read operation from that internal address from that slave. What matters is that this whole driver that I wrote in C++, it is enough to use I2C to access sensor information from this small module via I2C protocol. And here's the header file, and there's also a C file with extra details and extra function calls to talk in I2C from the Raspberry Pi 5 to a device. The other very important remark on the driver level, so we're still speaking about the driver, is that I'm using Linux. Of course, the Raspberry Pi 5 is a Linux device, and it has a specific I2C API, which is very nice. It's very easy to use, convenient, nothing complicated at all. That library is called I2C/SM Bus. There's a very nice documentation page on that library. Just reading this landing page, if I remember correctly, the landing page was sufficient for me to write all the functions that I needed to write. Because I2C is supposed to be very simple. All you need to know is, what is my slave address that we just saw? What is the register that I want to access? Do I want to read? Do I want to write? Do I want to read in a bulk or write in a bulk? That's all you need to know. It's a very simple protocol. It's a very simple interface, and the Linux provides these functions as an API to get to use I2C methods from your Raspberry Pi 5 to a device. And this is the low-level interface. It's just like this. You have a file that you open prior, then you want to send, read or write a specific data to a specific address, and then you return that value. And that's it. That's all you have to do. And if it's a stream block, you pass how much bytes you want, how many bytes you want to read, where to store them, and that's it. It's very straightforward. So if you want to know more about I2C, I invite you to read that specific file. It is very simple. And here, in the rest of the file, we just do the various operations on I2C level to talk to this device, configure that to use a specific scale, a specific frequency of sampling, and other things. Then we look into the server. The server is an object, and the object holds a service. The service is the very cool part about this. So we use in gRPC. Like I said before, this gRPC is basically writing a file like this, an interface definition file, and this establishes the contract, this establishes the functions that you can call, establishes the messages, the contents, the types, everything. This is what any other client from multiple different languages can also use to generate their stub definitions, and then they can consume the data that we provide as server. We as servers use the same protofile to generate the services like this. We inherit this class, which is generated by Proto, the compiler, and all we have to do is write those methods. In our case, for today's video, this is the important method. Get IMU. This is what the client, consumer of data, will call. And in this case, it's going to open a stream, and then the server will stream IMU data to that client. Here's a little bit on the details on what we actually do whenever a client calls this. We do some pre-checks, and here we have sort of a loop. We check, has the client gave up already? Is the context of the communication canceled by either myself or the client? No. Therefore, I'm going to do another loop. I'm going to check if the queue, so my server, if we go back here, it contains a queue, IMQ, which is just a buffer of data that we retrieve from the sensors. Some application, some other object or component has to put sensor data inside that queue. That's why we have a method called put_IMU_data. This is not seen by the client. This client is an external device calling this. This is by our internal application. So this is probably what's the driver gonna call. So more on that later. Back to the service. If there is an object in the queue, we just convert it to gRPC, to the message defined by the proto file, and then we write to the sockets or to the communication. This is the time where the data is streamed over to the client. Exactly when we do this write. And lastly, the publisher application, which is the main application. It is the thing that holds everything together. It's the thing that creates all the objects and passes data along them. This is the main. This is where we start. There's a function that I call real-time priority. This is something I've shown in a previous video. It's not strictly needed. It is just gonna guarantee a small latency for this module. Then we have an I2C device that we pass via a command line to this program. This is the inputs to our class, the IMU class, the driver class. And this is basically a path in Linux pointing to the device, to the actual I2C hardware that lives in the board. Then we pass a slave, which is the address of this guy. Initialize the drive, we do some calibrations, some very simple functions that I wrote to make the data a little bit nicer. Then we start the server, which is basically spinning up the gRPC server, registering the scan service, which is what is servicing the methods for the gRPC from the proto file definitions. Then we just loop. That's all. We just loop. Every time we wake up from our sleep, we check, give me new data from the driver, then we publish to the server, the queue is appended, and if any client calls at that time, the queue is going to be streamed over the client. So we're going to be pushing to the queue, and the queue is going to be streamed over to the client. All we do. Very decoupled, very nice, elegant, zero stress. Now, you're probably wondering, or not, how am I going to deploy this in a Raspberry Pi 5? Because so far, you've just shown this is a cool code, it's C++. Maybe I know a lot already about this, but I'm wondering, how do I deploy this in a Raspberry Pi 5? The answer is Docker. With Docker, we can build this as a standalone executable, push it to some registry, and from the Raspberry Pi 5, all we have to do there is install Docker, pull from the registry, run it, and there we go. We are ready, and we would be already publishing and communicating continuously with the sensor and publishing data to any client that has interest on all the data. But does it really work? Because the Raspberry Pi 5 is going to communicate with the device that is via cable, so there are wires here. How does Docker work with wires? It just works. Docker allows you to pass a command line option that mounts a peripheral from the host into the Docker container. So the Docker container has full access, for example, to I2C devices that lives in the board. It's very straightforward. Let's see that in action. Here we are with the Raspberry Pi. I've just logged in, and the very first thing I want to show you is there is a package which is already installed, but I'm going to show you how to install it anyway. I2C Tools. This package provides command line tools to scan your I2C bus for a slave device. I've purposely disconnected the bus, and this is the command that you're gonna see that you can use to detect what devices are connected to each bus. So I know that these two particular pins refer to the I2C bus 1. If I do this, I don't see anything, and if I connect them here and then I scan my bus again, we're gonna see here there is a device detected which has slave address 69. Perfect. The I2C device in Linux lives in this folder, more specifically like this. The Raspberry Pi contains 1, 13, and 14. 1 is this one, 13 or 14. I'm not sure where they are. Maybe they are internal. Doesn't matter for now. But this is the typical I2C device in a Linux operating system. Another check for the Raspberry Pi is you do this as config. Make sure this is enabled. If you go to interface, I2C, do you like I2C enabled? You say yes, then it's enabled, and it's gonna persist among boots. So if you don't see that device here, it can mean that it is because the Raspberry config was not configured to expose I2C. Okay, let's start the IMU streaming server. So the way we've done here is using Docker. So I'm not going to go into much details into that now. What matters is that we've produced an executable. We can build it, and in the same repository there is a place. There's a documentation how to push your Docker image somewhere, and here we're just gonna pull it. And that Docker image is called like this: Docker pull. This is my personal registry, ICM. This holds the application that we just spoke about. Everything that we just saw on the IMU, the driver class, the publisher class, everything is inside that container. So just to be clear, fully clear, this publisher is the entry point of that Docker image. And just to give you a hint, This is the Docker file that builds that application. I'm not gonna go into much details now. What matters is that if essentially this is what I'm gonna call now. So I'm gonna make this small again. So the way we're gonna start our server is like this: Docker run. Then I'm gonna do init. Then the first process is attached to my executable. I don't want it to keep the container. I'm gonna publish port gRPC port. This is the important part. I'm gonna mount the I2C device. I2C. Let me put this here. Dev I2C 1, and then we're gonna call my container that I pulled and say 90. Right. That should be it. I only say these print lines if I know it works. So apparently it did work. Currently, my Raspberry Pi 5 is getting the IMU data and publishing to my server. To consume that, I've also written a client in Python. It lives right here, test client IMU Vis, which I'm gonna call from my MacBook like this. So I've just pulled another terminal. This terminal is native to the MacBook. I've installed these requirements. I've generated the proto files. There's a README file teaching how to do that. And then this is the basic application. I point to the Raspberry Pi. I create a matplotlib window, and then as I get streams, I append to the underlying data map, and then it just renders them in real time. So enough of that. Let's call it Python client IMU Vis. This is gonna connect to the gRPC server, and we're gonna start seeing data streams of inertial sensors. That's how it looks like. If I move this guy, you can see it's quite sensitive. Front back. I can make it bigger. Front back. Side. Up down. I accidentally hit the table. Rotation. So on the bottom here, this is the gyroscope. You see the green is the Z-axis, so rotations around the Z-axis, rotation around the X, rotation around the Y. And very important thing here is that if you look at the accelerometer, you're gonna see that the modulus, so if you would, let's say, if you would take the squares of all the axes of accelerometer, you'd have what you want is the gravity vector modulus. So the square and the square root of the square of all the sensors of accelerometer should all be computed to 1g. This means, in other words, that whatever I rotate here, the modulus, the norm of that vector, should always be the same, because we cannot, at this moment, right now, we cannot be without gravity. So the gravity can be fully pointed to X, to Z, to Y, or to X. We cannot get rid of it. The accelerometer is always feeling the force of gravity. That's it for this video. I hope you have enjoyed it. I hope you have learned something new. Maybe you didn't know about gRPC, maybe you didn't know about I2C, or maybe you didn't know about inertial sensors. I hope in some level that you learned something new today. In the next video, I'm gonna show you how to process that information. So far, we've collected raw information from the sensors, so we've seen maybe we probably cannot make too much sense of this. How am I gonna use it for anything? In the next video, I'm gonna show you exactly how do I decode this kind of sensor measurements into angles. What kind of angles? What kind of errors can I get? What kind of precision can I get? What kind of different measurements from different sensor vendors can provide? All it in a next video. Thank you very much for watching. Until next time.